So our next speaker is Sou Tanaka from the Osana lab of the Kumamoto University. Sou is a second year's master student, and his research focuses on high throughput electronics and systems. And today he will present to us a serial communication IP which is vendor independent. Please, Sou, thank you. Thanks for coming.
Can you hear me? Okay. Thank you for your introduction. Hello everyone, I'm Sou Tanaka from Kumamoto University in Japan. I'm going to talk about Kyokko2 portable multi-gigabit. Oh, okay.
We can't hear you very well. Sorry about that. Right here? Or maybe this shape. Sorry.
Okay.
Is that working?
Okay. Thank you. I'm going to talk about Kyokko2 portable multi-gigabit serial communication controller for FPGA to FPGA communication. Recently, the development of quantum computing has been proceeding rapidly. In particular, fault-tolerant quantum computing require low latency processing and fast feedback of a large amount of measurement data. To support these requirements, FPGA cluster-based high-speed processing system are attracting attention. As a result, low-latency FPGA to FPGA communication is becoming increasingly important. However, standard protocols such as Ethernet and Interlaken can be used for FPGA communication. However, their protocol introduce relatively large overhead and latency. So, for lower latency communication, FPGA vendors provide lightweight serial communication IP. For example, AMD provides Aurora, and Altrera provides Serialite. However, these protocols are vendor-specific, making interoperability across FPGA vendor difficult. In addition, their extensibility is limited. To address these problems, our laboratory developed Kyokko, a vendor-independent serial communication controller. Next, I'll explain Kyokko. Kyokko is our open-source implementation of the Aurora 604b66b IP protocol. It separates the device-independent protocol layer from the device-specific transceiver interface, using wrapper module to hide interface differences and enable portability across multiple FPGA vendors. We have also confirmed that Kyokko achieves lower latency communication than the original Aurora 604b66b IP. The original Kyokko architecture assumed transceiver with an asynchronous gearbox. Next, I'll show the latency evaluation result. We compare the communication latency of Kyokko and Aurora on several FPGA platforms. On the AMD Kintex ultra-scale platform, Kyokko achieved lower latency than Aurora. We also evaluate Kyokko on Intel transceivers such as Ariel 10GX and Stratix 10GX. These results show that Kyokko can achieve relatively low latency across multiple FPGA vendors. In particular, Kyokko provides lower latency than the standard Aurora IP while maintaining Aurora compatibility. Next, I'll explain gearbox operation. And the figure assumes 10G communication using 604b66b encoding. First, let me explain the asynchronous gearbox. In an asynchronous gearbox architecture, the user logic side and the service side operate in different clock domains. In an asynchronous gearbox architecture, the gearbox internally absorbs the interface-wise and clock differences. As a result, the user logic can continuously transmit data without invalid cycle. This is a major advantage of asynchronous gearbox operation. However, supporting different clock domain makes it difficult to operate at higher frequency. Next, I'll explain synchronous gearbox architecture. The user side and the server side operate with synchronized clock. And because of the 6-4-6-6 rate mismatch, invalid cycle periodically appear during transmission. This is a disadvantage of synchronous gearbox operation. On the other hand, synchronized operation enables higher speed communication. This table shows the recent trends in modern FPGA transceivers. Looking at AMD transceiver GT8, GTY, and GTYP support asynchronous gearboxes, while the newer GTM transceiver, which target higher speed communication, doesn't support asynchronous gearbox operation. Similarly, Altrera transceivers such as E-tile and F-tile also don't support asynchronous gearboxes. As communication speed continue to increase, modern transceiver trends to omit asynchronous gearbox support. To current Kyokko architecture assume that the transceiver includes an asynchronous gearbox, which makes it difficult to port Kyokko to newer transceivers that don't support asynchronous gearbox. Therefore, in this work, we developed the Kyokko2, a vendor-independent Kyokko2, a version of Kyokko designed for synchronous gearbox operation. This slide shows the architecture of Kyokko. Kyokko is mainly divided into two parts: TX control, which manage data transmission, RX control, which manage the data reception. The colored region in this diagram represent different clock domains. The pink region in the upper left operates in the receive clock domain. The receive clock is recovered from the incoming serial data. The other blue region operates in the transmit clock domain. This slide explains the transmit side interface in more detail. A serial communication can be broadly divided into two phases: link initialization and data transfer. The orange arrow represents link initialization, and the green arrow represents the data transmission. And before the communication link is established, the state machine inside TX controls sends control data for link initialization. After the link is established, user data is transmitted from the application side. On the receive side, the clock must be recovered from the incoming serial data. However, if the transmit data contains long sequence of only 1 or 0, that there may not enough signal transition for stable clock recovery. To avoid this problem, the transmit data is scrambled before transmission. Next, I'll explain in a receive side interface in more detail. Similar to the transmitter side, the orange arrow represents link initialization and the green arrow represents data reception. Since the received data is scrambled, it must be first be descrambled. Before the communication link is established, the received data is handled by the RX control block. Once the link established process is completed, the channel up signal is asserted. After channel up signal is asserted, the descrambled data passes through an asynchronous FIFO and is transmitted to the user logic. This asynchronous FIFO observes the clock domain crossing between the receive clock domain and transmit clock domains. The original Kyokko architecture assumed asynchronous gearbox operation. As a result, continuous data transmission was possible without considering invalid cycle. To address this issue, we introduced valid-based control. The figure on the right shows, however, to support synchronous gearbox operation, additional control logic is required to handle the periodically occurring invalid cycle. To address this issue, we introduced valid-based control. The figure on the right shows a simplified overview of this valid-based mechanism. Valid is a signal that indicates whether transmitted data is current cycle is valid or not. This slide shows the Kyokko2 architecture. The modifications from the original Kyokko are highlighted by orange arrows. In Kyokko2, invalid cycle required for synchronous gearbox operation are handled on the transmitter side. Since invalid data is prevented from being transmitted, the receive side doesn't require major modification compared with the original Kyokko architecture. This slide shows the invalid cycle aware transmit control mechanism in Kyokko2. Inside the transceiver, transmitted data becomes invalid when the cycle count reaches 32. Therefore, Kyokko2 must avoid transmitting user data during these invalid cycles. The scramble provides the cycle timing information used for transmission control. When valid is deasserted, the TX controller inserts a control block instead of user data. At the same time, the scrambler temporarily stopped updating its internal state. In this way, Kyokko2 handles invalid cycle during transmission. Next, I'll explain the hardware implementation. In this work, we implemented Kyokko2 targeting the A-Links AXKU042 FPGA board. The board uses a Kintex ultra-scale XCKU040 device equipped with GTH transceivers. And there are the simulation results. In simulation with AMD Aurora 6OB66B IP as the communication partner, we confirmed successful channel application on both the Kyokko2 side and the Aurora side, indicating successful link establishment and data transfer. Next, I'll discuss future work. In this work, we implemented Kyokko2 on AMD GTH transceiver and confirmed successful communication with Aurora in simulation. We believe that hardware implementation should also be feasible for GTH and GTY transceiver in the future. Going forward, we plan to extend support to newer AMD transceivers such as GTYP and GTM, as well as Intel and F-type transceivers. In particular, one of our future goals is to develop a portable 6OB66B gearbox for Kyokko2. This will enable support for Intel F-type and wider range modern transceivers. Finally, I will conclude this presentation. We developed Kyokko2, a version of Kyokko designed for synchronous gearbox operation. Specifically, we redesigned the original Kyokko architecture to support control mechanisms that handle invalid cycle caused by synchronous gearbox operations. In simulation with Aurora, we confirmed successful link establishment and data transfer. As future work, we plan to extend Kyokko2 support to AMD GTYP GTM and Intel F-type transceivers. I would like to acknowledge the support for this work. Thank you for your attention.
Thank you very much, Sou, for this very interesting talk. Do we have any questions, please? Please.
Hi, and thanks a lot for the talk. Your numbers are I think, roughly 100 nanoseconds better than Aurora in terms of latency. Do you have any comment as to why that is? Like, what do you do better that Aurora does not do? Why they're so much worse?
Thank you for your question. You mean like the Kyokko, why Kyokko so faster Aurora? Yes. I have no idea this question because the Aurora is IP, so this is a black box. So maybe Kyokko Aurora has more. Aurora may contain additional internal logic used to buffering that are unnecessary in our use case, and could continue to sorry. Maybe Aurora has more additional logic in Kyokko.
Maybe I can comment on that. And also, it's kind of related to a question I have for Sue. Do you support multiple channels or just a single one? So you have one core per channel. Is that what you have?
Sorry?
So your IP core supports one single transceiver?
Yes.
So maybe this is partially related to the previous question because Aurora has this, let's say, feature to group multiple transceivers together with one IP. So maybe part of it is connected with that. Maybe Professor would like to comment on that, Professor Osana?
Yeah, I think I have to help him. So in original version of Kyokko, we support channel bonding. Yeah.
Professor.
So in original version of Kyokko, we already has support for channel bonding up to maybe 8 lanes, but his version still don't have one. So maybe the next student will do that next year.
Any other question, please?
Yeah, so you mentioned you have a max speed of 10 gigabit, right? Did you test any higher speeds as well?
Sorry?
Did you test any higher speeds than 10 gigabit as well?
Did you test?
Any higher speeds than 10 gigabit? What did you test?
Did you test?
So you mentioned in this latency measurement, you tested the protocol at the rate of 10 gigabits.
10 gigabits.
Did you try any higher speeds on your gigabit transceivers?
Yes. We did in 25 gigabit. Yes.
Okay. And if I may, one more question. Do you also support half duplex operation?
You also support. Sorry, one more, please.
Do you support half duplex operation? So just if it's possible to configure your IP to be just a transmitter without a receive path back.
Without わかんない。
Yeah, this is kind of a common feature in some of our systems at CERN. We do often only transmit, and then we often only receive on the other side. So this is the question, right?
Correct, yes.
So yes, do you need a receiver to operate your system, or if you have just a transmitter, will it work? Will you manage to send data out without a receiver, or it's kind of necessary?
You mean flow control?
No. Yeah.
Yes.
Or do you have perhaps options to just use some sidebands or whatever, sideband signals?
We have a flow control compatibility with Aurora.
Yeah, I guess we'll have to take that offline. Do we have time for another question? Please. Yes, please.
Hi. Do you have also some numbers on the serial light IP from Intel compared to the Aurora, because that you're not showing, right, on this one?
Serial light? Sorry? GRI protocol?
So
Yes.
like comparing the Aurora to the serial light from Intel.
No. This Altrera FPGAs use Kyokko only Kyokko's latency, and this so light blue is Aurora, so blue is Kyokko, so no shear light latency.
Yeah, sorry, it's my fault. So actually, we have a figure for serial write, but I lost in the graph.
All right, that's another thing to discuss during the coffee break. Do we have a time for maybe a last question? Yes, please, at the back.
Thank you for the talk. What kind of interfaces are supported? I saw that SFP is supported. What are the interfaces are supported in this protocol?
What support?
Does it support Ethernet? Like any other? Oh, sorry, not Ethernet. Sorry. Yeah, physical. So.
Physical. インターフェースは何を使う
Okay. Thank you.
All right, so it seems we have to continue this discussion offline during the coffee break. Let's thank again our speaker.
Thank you so much.